So now we're going to work through a few example problems to illustrate some of our gas laws. And the first one asks, to what pressure must a gas be compressed to get it into a 3.00 feet cubed tank if it occupies 40.0 feet cubed at 1.0 atmosphere? Assume the temperature remains constant. So if we read through this will be a direct application of Boyle's law. And Boyle's law says that P1 times V1 is going to be equal to P2 times V2. Okay, so sometimes it's beneficial to write down the constants that we have and the things that we're going to try to find. So our initial pressure that we start with is 1.0 atmospheres. The second pressure is what we're going to try to solve for. Our initial volume is 40.0 feet cubed, and our final volume is 3.00 feet cubed. Okay, so if we plug these values into our particular expression, we'll see that 1.0 atmospheres times 40.0 feet cubed is going to equal P2, which is what we're trying to solve for, times our second volume, which is 3.00 feet cubed. All right, if we solve for P2, we can rearrange this expression to get 1.0 atmospheres times 40.0 feet cubed is going to equal 3.00 feet cubed. Our feet cubed units are going to cancel, and we're going to be left with atmospheres, and our final answer will be 13.333 atmospheres. So if we look at the number of significant figures that we have two significant figures with 1.0 atmospheres and three significant figures from 40.0 and 3.00 feet cubed. So we're going to have to express this answer to two significant figures, which will be 13 atmospheres. So now let's kind of look and let's see if this answer makes sense. So we're starting out with 1 atmosphere of pressure, and we have a fairly large container. Okay, we are going to compress this from 40 feet cubed all the way down to 3 feet cubed. So if we're going to compress this gas to a smaller container, we expect the pressure to go up, and since we have a fairly large change in volume, we're going to expect the pressure to be much larger in this case. And we go from 1 atmosphere to 13 atmospheres, so this answer would indeed, make sense. So whenever you're solving problems here, don't just think about solving them numerically. Think about getting an answer that makes sense by looking at what you start with and what you finish with.